For over a century now, we've basically had a superpower, the ability to see inside things without ever cutting them open. It all started with those familiar, kind of spooky images of our own skeletons. But what if we could zoom in, like way, way further? What if we could actually film the tiny molecules that build our entire world and watch them work in real time? Well, that's exactly the journey we're going to take today.
So, our journey kicks off with something you've probably all seen before, a medical X-ray. It's a piece of tech that's so common, we almost take it for granted, right? But think about it. It's the power to make our own bodies transparent, to see the solid bones inside. This is our starting point, our baseline, our first step into a world that's totally invisible to the naked eye.
And that right there brings us to the big question. I mean, we've totally mastered seeing the big stuff, bones, fractures, that kind of thing. But the real action, the actual dance of life, it's all happening on a scale that's billions of times smaller. So the question is, how in the world do you go from a still photograph of a skeleton to a live-action movie of a single protein doing its job?
All right, to figure that out, we've got to go back to square one. We need to understand the original magic trick. So, let's do a quick breakdown of how a classic X-ray actually works.
Okay, so the fancy term for it is radiography, but the concept itself is, well, it's beautifully simple. You just fire a special kind of energy, X-rays, at something, and then you basically just see what manages to get through to the other side. That's it.
The easiest way to think about it is like a shadow photograph. It's super intuitive. Your bones are dense, right? So they block a lot of the X-rays, and that casts a really clear shadow on the film. But your softer tissues, they're less dense, so more of the X-rays just pass right through, which makes their part of the image lighter. Simple, elegant, and yeah, it absolutely changed the world of medicine.
Okay, so a shadow picture of a bone is one thing, but what if you want a picture of something ridiculously small, like a single atom? Well, for that, you're going to need a much, much brighter flashlight.
And believe it or not, this idea isn't new at all. Scientists were using X-rays way back in the day to make one of the biggest discoveries ever, figuring out the double helix shape of DNA. But the tools they had back then were, by our standards today, incredibly weak. To get a really sharp picture of these tiny, tiny structures, they needed a massive leap forward, a real game changer.
And that leap forward, it came from a massive machine called a synchrotron. Now, the key difference here isn't just about raw power. It's about a special quality called brilliance. The best way to picture it is like this. A normal X-ray machine is kind of like a bare light bulb. It scatters light everywhere. A synchrotron, on the other hand, is like a super-focused, super-intense laser pointer.
So how does this gigantic thing even work? Well, at its core, a synchrotron is basically a huge racetrack for particles. It grabs electrons, cranks them up to almost the speed of light, and then, this is the cool part, it uses a series of powerful magnets called undulators to make them wiggle back and forth really, really fast. And every single time one of those electrons wiggles, it shoots off a tiny bit of energy. And that energy is an intensely bright, perfectly focused beam of X-rays. All right, so now we've got a flashlight bright enough to see individual atoms. Awesome. Problem solved, right? Well, not quite. What about seeing them move? That's the next great frontier. Because if you think about it, chemistry, biology, none of it is static. It's all about motion, and incredibly fast motion at that. So here's the problem. Our amazing synchrotron has a speed limit. The camera flashes it produces are about 50 picoseconds long. Now, a picosecond, that's a trillionth of a second. That sounds insanely fast, doesn't it?
Well, to a molecule, 50 picoseconds is an eternity, a complete lifetime. The most basic things that atoms do, like a chemical bond breaking or a protein snapping into shape, can happen in just 30 femtoseconds. And a femtosecond is 1,000 times faster than a picosecond. We're talking about two totally different universes of speed here.
You see the problem? We've got this massive mismatch. Trying to take a picture of a 30 femtosecond event with a 50 picosecond flash, it's like trying to get a sharp photo of a hummingbird's wings with an old school camera on a slow shutter speed. You're just going to get a blur. The tool was just way, way too slow for the job.
So what do you do when your camera's too slow? You build a better one. Science built an entirely new kind of machine, one that could create an X-ray flash that was finally fast enough and bright enough to freeze the motion of atoms dead in their tracks. This is the ultimate strobe light.
It's called a free electron laser, or an FEL, and it starts out a lot like a synchrotron, actually. You accelerate electrons and you wiggle them through magnets. But here's where the magic happens. Inside an FEL, the wiggling electrons start to interact with the light they're creating. This causes them to bunch up, to get organized, at the exact same wavelength as the X-rays. And then, these bunches all release their light at the exact same instant, in perfect unison. What you get is a single, coherent, mind-blowingly bright, and unbelievably short pulse of X-ray laser light.
And the jump in power here, it's almost impossible to wrap your head around. Seriously, if the synchrotron was a laser pointer, a free electron laser is like the Death Star. Its brightness is about 100 million times greater than even the best synchrotron out there. It's a completely staggering increase in power, and it finally gave us a flash that was both bright enough and fast enough to get the shot.
Okay, so we've got the tool. We have a camera with an impossibly fast and incredibly bright flash. The question is, how do you actually use this thing to make a movie of a chemical reaction?
The method they came up with is called pump probe, and it is just so clever. It all comes down to two separate pulses of light. The first one, the pump, is like a starting pistol. It's what kicks off the chemical reaction. Then, the second pulse, the X-ray probe, comes in just a fraction of a second later, at a very precisely timed moment, to take the picture.
Here's a great way to think about it. Imagine you want to make a slow-motion video of a balloon popping. The pump pulse would be the pin you use to prick the balloon, and the probe pulse is your camera's flash. To make the movie, you do the experiment over and over, but each time you delay the flash just a tiny bit longer. The first time, the flash goes off the instant the pin hits. The next time, it goes off as the rubber just starts to tear. The next, as the air is rushing out. You take all those individual pictures, you stitch them together in order, and boom, you've got a slow-motion movie of the balloon pop. Well, scientists do the exact same thing, just with molecules instead of balloons.
You see, this ability to film molecules while they're moving, it's not just some cool science trick. This is a fundamental shift. We're going from guessing what's happening down at the atomic level to actually watching it happen with our own eyes. And that opens the door to a completely new era of discovery.
So, what's the big deal? Why does this matter to you and me? Well, think about it. By seeing exactly how photosynthesis works step by step, we could learn how to create super-efficient solar panels. By watching catalysts do their thing, we could design cleaner, better fuels. We could invent brand new ways to store massive amounts of data, or finally pinpoint the exact molecular screw-ups that lead to diseases. For the very first time, we can pop the hood and watch the engine of nature while it's actually running.
For the first time ever, we're not just staring at the blueprints of the molecular world, we're on the construction site, watching it all get built in real time. This gives us a power we've never had before, the power to truly understand and, maybe one day, even direct how our world is put together, right from the atomic level. Which leaves us with one heck of a question. Now that we can finally film the building blocks of reality, what are we going to build next?